Hi everyone, my name is Yuan, and I'm a principal software engineer at Red Hat working on OpenShift AI. I'm also a project lead for Argo and Kubeflow. Today I'm going to talk about engineering cloud-native AI platform. The AI landscape and ecosystem have been rapidly growing ever since the birth of large language models. You can check out these different landscapes from Linux Foundation or CNCF for more details. Some example projects include Kubeflow and Argo and KServe from infrastructure side, and TensorFlow and PyTorch from machine learning frameworks perspective. Next, I'm going to talk about different elements to consider when building production-ready AI platform. The first is scalability. In terms of scalability, there's horizontal scaling and vertical scaling. Horizontal scaling means that you're adding more pods and machines to handle additional workloads. Vertical scaling means you're adding more computational resources such as memory and CPU and GPU to existing pods to handle additional workloads. And there's also cluster autoscaler that can adjust the size of your Kubernetes cluster automatically based on your workloads. And algorithm scalability is also something to be considered as well. Sometimes you need to modify your algorithm to be scalable enough to handle online fashioned workloads. And hardware acceleration and resource sharing and scheduling are also important in order to fully leverage the benefits of hardware acceleration. The next element is reliability. So you may want to make sure that your cluster and your AI workloads can be highly available and can handle any disaster situations. For example, if you are building a Kubernetes controller, you may want to support leader election. In case of any disasters, you can recover from where it's left off. And you may want to follow GitOps principles so that if any disasters happen, everything can be restored following the source of truth on GitHub. And you may also want to consider preventing from being locked in by different vendors and consider using hybrid cloud. And also, if you are using a lot of technologies and have a lot of dependencies, consider whether those technologies are being supported by a particular vendor, or do you have any SLAs and so on. The next element we want to consider is observability of your AI platform. So you may want to look into different performance metrics in terms of statistical and operational. Statistical metrics include like hyperparameter tuning metrics for experiment tracking, and operational metrics include system metrics like computational resources and so on. You may also want to explain what model is being built and whether the model is trustworthy and why the model is generating a particular prediction. And you also want to visualize the model training progress, and you want to visualize what's happening in your pipeline, who's building what model, who's using this data set at what time, and so on. The next element is flexibility. Whether your AI platform supports multiple machine learning frameworks like TensorFlow, PyTorch, and XGBoost, or whether it only supports one model framework, and whether your data science team needs different language SDKs, or whether they need like a standardized APIs such as OpenAI APIs for model inference. And what's the nature of your data and your model? What are the sizes of your data source and your model? Whether they are streaming or batching, and whether what framework is used to build the model, and whether your model performs well with that particular framework. And also consider how your AI platform can be integrated and leverage hardware accelerations, and where your workloads are running, like on the cloud or on-prem or on the edge, and whether your platform is locked in by a particular vendor. Before diving into each different components of an AI platform, I'd like to first introduce Kubeflow. Kubeflow is the machine learning toolkit for Kubernetes. It contains different components such as Jupyter notebooks and Kubeflow pipelines, central dashboard, and training operator for distributed model training, and Katib for experiment tracking and hyperparameter tuning, and KServe for model serving. And it also supports multiple machine learning frameworks and on different environments like Kubernetes, on-prem, or in cloud. The first component in a cloud-native AI platform is usually the data processing component. And here we are only focusing on big data technologies because that's the one who can fully leverage the distributed computing power of Kubernetes. Apache Spark is one of the example technologies that we are using here, and it supports both batch and streaming and time series. And we'd also like to welcome the Spark operator to join the Kubeflow as a sub-project. On the right-hand side, you can see a simple YAML specification that defines a distributed Spark application that can be submitted easily to the Kubernetes cluster via the Spark operator. Kubeflow training operator is one of the core components of Kubeflow, and it supports submitting distributed model training jobs to Kubernetes using different machine learning frameworks like XGBoost, TensorFlow, and PyTorch, and it has both Python SDK and APIs. And it supports multiple distributed strategies like all reduced style training with MPI, and also like parameter server-based distributed model training. It also supports different job scheduling frameworks with Volcano and Q, and it also supports elastic training. This is the architecture diagram of the training operator to submit a distributed model training job with TensorFlow. So what the training operator does is that it sets up all the necessary environment variables required by TensorFlow, and also creates the necessary workers and parameter servers on Kubernetes, so that users only have to define how much resources they want to use and what training code they want to use in Python. Next is the model tuning component, and Katib is one of the core projects in Kubeflow that supports hyperparameter tuning, neural architecture search, and early stopping. It is also agnostic to different machine learning frameworks and different programming languages. And because it's built on top of Kubernetes, it can be deployed anywhere from local machine to private or public clouds, and it can natively integrate well with other Kubeflow components like notebooks, pipelines, training operators, and so on. This is a screenshot of the Katib UI where you can see all the different hyperparameter tunings and their relevant performance that contribute to different variations of the model. Once you have trained the model and tuned your model using Kubeflow training operator or Katib, and the next component and the next step is the model serving step. You want to serve the model in a scalable fashion. So KServe is one of the project that's graduate from Kubeflow that provides highly scalable, standard, and cloud agnostic model inference platform on Kubernetes. It provides standardized inference protocols across different machine learning frameworks. It also supports serverless workloads with request-based auto-scaling, including scale to 0 on both CPU and GPU. And it also supports highly scalable density packing and intelligent routing using model mesh. And it is also simple and pluggable that can be used for different phases of the inference. For example, you can insert different pre-processing and post-processing into the model serving and continuously monitor your model performance. And it also supports advanced deployment strategies such as canary rollout, and also supports pipeline and ensembles with inference graph. KServe has unique strength for building a distributed inference graph, an auto-scaling graph router, and native integration with individual inference services, and a standard inference protocol for training multiple models. KServe leverages this strength to build an inference graph and enable users to deploy complex machine learning pipelines inference pipelines to production in a scalable way. For example, you can use the ensemble node to ensemble different models separately and then combine the result into a single prediction response. You can also use a splitter node that allows users to split the traffic to multiple targets using a weighted distribution. Canary rollout is one of the rollout strategies we support in KServe. It's important because data scientists often iterate models on different versions, and they don't want to break everything at once by just upgrading the models directly. So instead, they can use Canary rollout to gradually split the traffic between the old versions of the models and the new versions of the model, so that if any bad things happen to the new versions of model, they can automatically roll back to the previous version. Being able to explain the models you build is also important. KServe supports pluggable explainer runtimes so that you can explain and answer questions like, why did my model produce this inference result? The next component in a cloud-native AI platform is a workflow component. Argo Workflows is the container-native workflow engine for Kubernetes. It's a generic workflow engine that can support multiple use cases such as machine learning pipelines, data processing, infrastructure automation, and continuous delivery. Argo Events is the event-driven workflow automation framework. It supports over 20 event sources and over 10 different triggers. You can use it to manage everything from simple, linear, real-time to complex multi-source events. And it's also compliant with cloud events specification. And here's a reference workflow for cloud native AI platform, assuming you want to monitor GitHub events, and whenever there's any changes on GitHub, you want to use Argo to trigger a workflow that starts with the data processing step, and then using TensorFlow and Kubeflow training operator for distributed model training, and then using Katib if you want to fine tune the model and do some hyperparameter tuning or architecture search. And then at the end, the trained model will be served by KServe. Once we have built the AI platform using the cloud-native technologies that I mentioned earlier, data scientists can then iterate on their experiments to build better models and better AI applications. Feel free to check out my book if you want to learn more about reusable and practical patterns that can be used in building a distributed machine learning system. If you have any questions, you can find me via any of the social platforms listed here. And thank you for listening.